So remember that, that a photon has a magnetic and electric field that it's propagating as it moves along in space. So a photon comes along, comes very close to the electrons of a molecule, and it's going to start tweaking them to a higher energy. That's really all that we're talking about. Is it ends up kind of interfering with them a little bit. You pull into a higher orbital. And we'll see an example of that here in another video. Now, for pulling it up to a higher orbital, keep in mind that what I'm implying at that point is energy. And yeah, that probably means that there's going to be some sort of a radius aspect as well, but it's not really what we're focusing on. Now this x-axis is an entirely arbitrary one, just for me to keep track of things and be able to separate them out in space a little bit so we can actually sketch things and visualize them. The y-axis, though, is actually going to be some sort of an arbitrary energy axis, probably in kilojoules per mole or something like that. We're not going to worry too much about having numbers on this. Now, let's just say that our ground state is right down here. And let's say that in this ground state, we have a well paired up orbital. So we have an up spin and a down spin to start with. Now, if you have paired electrons, we call that a singlet state. You don't have to worry too much about why. We just call them singlets. Since this is the ground state, we'll go ahead and we'll denote it as singlet 0. So down here in our S0, we've got some electrons. All right, now what can happen? Well, we know that the singlet state is going to have a whole bunch of vibrational levels as well. Because we know vibrational levels, they don't take as much energy. Let me go ahead and just switch to another color, try to help them be distinguishable a little bit. So I'm just going to put a whole bunch of vibrational states for the singlet 0. They're supposed to be more evenly spaced than they are, but you know, what can you do? Alright, so we got a whole bunch of these vibrational states. Now if I give it a small photon, and in fact, let's go ahead and say these are rotational and vibrational states together. That's probably even more authentic. That means that if I start hitting it with microwave radiation or radio or something like that, then I'll be just exciting through some of these. And then it'll just fall right back down. But way up here, I'm going to have an excited singlet state. And it's going to have its own little rotational and vibrational states. Just to have them distinguished, I'll go ahead and I'll put the red ones up here. Now that said, there's probably going to be more of these blue states extending all the way up here because we can keep on making this thing vibrate like crazy, right? So we're going to have a whole bunch of these states at once. Now suppose that this molecule absorbs a photon that had enough energy to promote this electron up to, let's just say, here in the singlet 1 range. That's going to be an allowed transition because it is actually ending up in an orbital right up here. It's going to have the singlet 1 vibrational and rotational character. You know, we could figure out exactly what all of them are, but we'd find out, okay, this is what it's doing at this point. Then, of course, what's going to happen? Well, it's in an excited state. It's going to give some of that energy off vibrationally, and we usually do that with the little wiggly arrow to show that it's vibrational energy. And it's going to relax by giving heat off. Now remember, if it's vibrating, it's banging into its neighboring solvent molecules. And so it actually is giving that energy off as more kinetic energy to its neighbors, and when everything increases kinetic energy, we call that heat. So fine, we're parked here in the singlet 1 state with my electron. I'm going to go ahead and cross it out as I go, just so we see what I'm talking about as I go. Now notice, I still have my spins paired up. I have one up spin, one down spin. You can think of the quantum numbers as being plus 1/2 spin and minus 1/2 spin. Well, what can happen to it from here? Well, notice that this singlet 1 state is going to match up with some of these vibrational levels of the singlet 0 state. So what can happen? The electron can just slide to the really excited state that's right there next to it. You can almost think of them as being the same building. It's just that you've got two different staircases built next to each other. You're just walking from one staircase onto the other and just continuing down. So, on down we go. Now let's complete things up a little bit. I said I put in this much photon energy in the first place. Remember that this is going to be a certain amount of energy, and energy equals h nu. We'll often just write h nu alongside of it to imply energy, and to imply that it's just going to be dependent on the frequency. Also notice that when it comes down, same thing is going to be true, but this is going to be a smaller energy transition than we had originally here, because some of that energy ended up as heat up here. Now, if every molecule follows this set of pathways, we put it up and then it just falls right back down these two staircases. It falls down to the singlet 1, then it falls down the singlet 0 vibrational staircase down to singlet 0. Everything ends up being heat. In other words, if we put in a quantum, in other words 1 mole of photons, we're going to have this much energy come out. Well, that means it's yielded 100% back out. So we call that the quantum yield, and we use this symbol. So quantum yield would be 1, as I've just described it. 100% of the energy that I put in just came back out as heat. Actually, we'll go ahead and just say heat right there. Now, let's get more specific here. Because if this is the only thing we have happening, then this description is going to do just fine. But if we're going to have more processes as a possibility, we're going to want to make sure that we can be very specific about it. So let me get my pen back. There we are. So what we're going to refer to this is going to be the internal conversion process. So we'll go ahead and we'll subscript that and say internal conversion, IC. So quantum yield of IC would be, in this simple case, 100%. But suppose that we're saying there's actually going to be more fates that are possible. So we're up here in the singlet state. We've already relaxed down to the singlet state, and that's always going to happen. So we're always going to get some heat on up here at the top. Now let's say the molecule decides to give off a photon. And in the process it comes down. And let's go ahead and get the blue one again. Remember, we still have those S0 vibrational states. These are the same ones as over here. My drawing skills just aren't that awesome. So we can jump back down. You can see that this is going to be almost as big of an energy transition as the photon we put in, but not quite as big. Let's extend this across too. When it gets in this excited state, it's still going to have to vibrate down a little bit, right? So we're still going to have a little bit of heat deposited at the bottom too. Well, what if it had only fallen down to here, or here, or any of the others? Well, each of those is also going to end up as heat, but notice that we have a whole different range of energies coming off. This process is called fluorescence because we're giving off a brand new photon, E equals h nu. It's going to be a lower energy photon than the one we put in. So if this was ultraviolet, then this one is going to be maybe violet, maybe blue, maybe blue-green for these 3 different arrows. And this also implies, though, that if I had originally, let me just kind of sketch up a spectrum up here. If I had originally put in energy at this ultraviolet wavelength, then what would have happened is it would have absorbed it, and then I would have it start emitting a whole bunch of light at some other wavelength. So this is just going to be intensity of light in or out. I'm just going to label it intensity very generically. In other words, I can take something under black light and I can have a bunch of bluish purple light start fluorescing off of it. Now please, don't misspell this and write it as flower. It's fluorescence, F-L-U-O-U-R. So, quantum yield of fluorescence. Well, this can't be 1 anymore because sometimes it's following this path, sometimes it's following this path. So maybe it's 80% of the time this way, which means 0.80. Maybe the other 20% is right here, 0.20 for this quantum yield. Okay, well, what other possibilities did we have? Well, we're going to assume that we didn't break any bonds. We're going to assume that we didn't burn out the molecule by breaking bonds. So we're going to just pretend no chemistry was occurring as a possibility. Well, I made a big deal of the quantum number right there, right? What if, and let me get a different color again. And I'm not implying anything about energies with these colors. I'm just getting some colors up here. All right. What if we had the electron flip its spin? So instead of it being an up arrow, it's a down arrow now. All right. What could happen now? We're going to have our vibrational levels on this one too. It turns out that if you have things where you have multiple spins of the same type, you call that a triplet state. So this will be an excited triplet state, and we'd have some lower energy triplet state too, presumably, but we're probably never going to see it because there's a singlet state in the way. All right, so we're going to have it sitting up here in one of these vibrational states. It's going to relax down by giving off some heat, and it's going to park that electron right here in the triplet state. So let me cross it off again since we've converted it yet again. After some amount of time, finally, the spin is going to flip back to upright, which is going to allow it to finally come back into this energy manifold. So I need my red pen. Here we are. So we still have our original ground state. Remember, we still have all those vibrational states on it. Yeah, there we go. Lots of vibrational states, just like we had back over here and here. So I guess I should have done that in blue, but we'll live with it. So now it can finally go through vibrational relaxation in the triplet state, or it can go and give that off as a photon. But notice it already lost some more energy up here. So this photon is going to be even lower in energy. It's going to stick around for a long time because it takes a while for this to be able to flip its spin again. So we have yet another quantum yield as a possibility for this process. This one would be phosphorescence. So phosphorescence, I'm just going to abbreviate it right there. Notice it's going to be an even lower energy. And so this is the fluorescence spectrum. Our phosphorescence spectrum is probably going to be out here. So if I take something like a glow-in-the-dark star and I stick it under ultraviolet light and it absorbs it, I'll probably get an immediate burst of fluorescence off it. So it's going to be glowing the whole time. And it's probably going to be glowing a more blue-green color. Then I turn off the black light, or I just take the star away. It continues to glow because some of those photons parked all these electrons up in the triplet state. It takes a long time for each of those electrons to flip back over in order to give off that energy as light or as heat. It finally manages to do so, so we get this profile. Now I'll point out the fluorescence is going to be way brighter than the phosphorescence. So this would actually be amplified by probably like times 1,000 for us to be able to have it on the same axis like this. And so you can see here it's also going to be more of a red shifted color. So the phosphorescent stars are probably going to be glowing at like a dim green color instead of a bluish green. So hopefully we're connecting some of this on the Jablonski diagram back to what we actually observe in our everyday lives. Now that's really what we're talking about for all of these different pieces of the Jablonski diagram. Now let's just hammer home the sort of times that we're talking about though for these processes. So for a photon to get absorbed, that's effectively an instantaneous process as far as we're going to be concerned about. The timetable for it to absorb is so fast that we won't care about it on the kind of time scales that we're ever going to talk about in an analytical chemistry course. Now, the lifetime is the term we use for it. Lifetime, we use lowercase tau. For fluorescence, that's usually going to be in the 10 to the negative 8, so 10 nanoseconds, to about the 10 to the negative 4, so maybe 10 microseconds, 100 microseconds, somewhere in that range. That's going to be the lifetime for this, and lifetime is kind of a messy term because remember, we have a whole bunch of these. They didn't all suddenly give off a photon at the exact same moment. There's going to be a time distribution of these. And so we will actually have a whole range for that. And it's going to be related to the natural log. The lifetime for it to decay, it's basically how long did it take for 1 divided by E to decay. So that's going to be the ratio for that. You'll still have things decaying probably out even at the 1 second mark. Not very many of them anymore, but you'll still have some. And so in a lot of ways it starts looking like radioactive decay, where half-lives and those sort of things. Now if you're getting out here to phosphorescence, the phosphorescence is going to be typically on the 10 to the negative 4 seconds through maybe 10 to the second seconds. So we're out there at the hundreds, maybe even thousands of seconds mark for phosphorescent materials. But even then, remember, over the entire time, every one of the ones you got up here and got over into this form, they're going to be slowly giving off some of this as energy, as light energy. So not only is it lasting a really long time, but it's now distributing all the light energy that you gave it out over very long periods of time. Glow-in-the-dark stars can never look anything near as bright as the original light pumping it, because it's going to have that time stretching effect of parking it for a long time and then finally relaxing after a while. If you want to have something that's bright, you're going to have to play some tricks. You might want to put like a radioactive isotope behind something that's able to glow so that it keeps on hitting it with photons or electrons or whatever, hitting it with energy, and as a result re-exciting them and giving them off. That's why you have tritium sites where you actually put some tritium behind the paint. As it decays, it hits the paint, and it basically goes through this whole process of fluorescence very quickly. Those really aren't glow-in-the-dark in the phosphorescent sense. Those kind of night glowing paints are a totally different thing. If you're going light in, these are the common fates to get back out. And we won't worry about a lot of the other ones. I just wanted you to be aware of the most common things we'd put onto one of these Jablonski diagrams, have some idea of the time scales involved, and some idea of what happens to the energy in terms of magnitude afterward as well.